Let's continue with another example. Let's suppose we want to find the derivative of the square root of x at x equal to 2. For f of x equal to the radical of x. Again, at this point, we are assumed not to know the formula, so we have to compute the derivative by using a definition. F prime of 2 is a limit, let's do a delta x notation, or instead of delta x, sometimes we will use h, so I'm going to use h. H goes to 0 of f of 2 plus h minus f of 2 divided by h. So in this case, it's a limit h approaches 0 of square root of 2 plus h minus square root of 2 over h. Again, if we examine this, we will see that this is an indeterminate form, right? Because the top goes to 0 and the bottom goes to 0, so you're required to simplify this expression and then take the limit. Notice that sometimes you might want to use the L'Hopital's rule on this, but not at this stage, because if you use L'Hopital's rule, then basically L'Hopital's rule requires you to take a derivative of the function on the top and the bottom. And in this case, we're trying to take a derivative of square root of x. And if you use L'Hopital's rule here, you'll have to take a derivative of square root of x. And so then this becomes a circular logic and you don't prove anything. So you cannot use L'Hopital's rule in this case. So this is a fairly standard example, and we know how to deal with it. In order to simplify, you need to multiply and divide by the conjugate. So square root of 2 plus h minus square root of 2 times the conjugate. And to keep things the same, divide, you already have h in there, and you have to divide by the conjugate again. And now we simplify the top. Limit as h goes to 0. Square root of 2 plus h squared, so that's 2 plus h, minus square root of 2 squared minus 2. Over h, or the sum of square roots. And so now h goes away as well, right, because we have h on the top and the bottom. And so 0 is gone from the denominator. So you no longer have an indeterminate form. And you're actually taking a limit of a continuous function, and the limit of a continuous function is equal to the value of that function at the point of the limit. So this is 1 over square root of 2 plus 0 plus square root of 2, 1 over 2 square root of 2 is your answer here. So f is differentiable at 2. All right. Okay, and so you see that if we try to find the derivative by using a definition, you'll always be dealing with questions like that. If a derivative exists, then basically always you'll have to take the limit of an indeterminate form, which you have to simplify, and then find the limit. If derivative exists, then you will be able to find the limit. So this was example 3. Now let's go back to the picture that I drew in the beginning of the previous lecture. We noticed here that if the function is continuous, it does not have to be differentiable, but we conjectured that if the function is differentiable, it should be continuous. And so we have reached the point where we can try to prove the statement. And I'm going to write it as a theorem. So, theorem. Suppose that f is differentiable at x equal to a. So the conclusion from this is that f is continuous. At a. And so let's try to verify this. So proof. So suppose that f is differentiable at a, or that the derivative f prime of a exists. So then saying this is equivalent to the fact that the definition of a derivative holds at a, right? So therefore f prime of a finite number, is equal to the limit x goes to a of f of x minus f of a divided by x minus a, and so this is a finite number. Okay, so then let's do the following. I'm going to multiply f prime of a by x minus a. And I would like to take a limit. Actually, let me do it in a different way. I'm simply going to try to take the limit as x goes to a of f of x minus f of a. If this limit is 0, right, then I know that the limit of f of x must be equal to f of a. So how do I know that? Is because by properties of limits, this is the same thing as a limit x goes to a of f of x minus limit as x goes to a of f of a, but f of a is a constant, so its limit is itself. So this limit minus f of a is the same thing as the limit I have written, that I wrote originally. Okay, so what can I say about this limit? I can say that I can use my usual example where I write 1 in some strange form. So for example here, if I have f of x minus f of a, I can multiply it by x minus a and divide by x minus a, right? This doesn't really change anything. And then I can rearrange this expression so that it becomes limit x goes to a, f of x minus f of a over x minus a, this limit I know exists, times x minus a. And the limit of x minus a exists, right? And it's 0 actually. So if both limits exist, then the limit of the product is a product of limits. This is the same thing as a limit x goes to a of f of x minus f of a divided by x minus a times the limit x goes to a of x minus a, right? And then this limit is easy to compute. This is f prime of a for the first limit and 0 for the second limit. So that means that the overall limit of f of x minus f of a must be 0. Let me get rid of this. Okay, and so from that, because limit of f of x minus f of a is equal to 0, it follows that the limit x approaches a of f of x must be f of a. And that's a definition of continuity at a. So f is continuous at a. So this is very easy to prove, in fact. One thing that I want you to recall and just keep it in mind. The opposite of this theorem is not true. And you just use a counterexample of absolute value of x. So, for example, absolute value of x is continuous at x equal to 0, but it is not differentiable at x equal to 0. Okay, so any differential function is continuous. Let's do the next. Prove the next set of properties of a continuous function. And let me just list them as a single theorem. Again, those are the properties that are familiar to you from the regular calculus. So that is the next theorem, properties of limits. Not of limits, of derivative. So here, let's suppose that f and g are differentiable at some x equal to a, and let's suppose that c, a real number, is a constant. So then, and I'm going to list all properties, and I'll prove actually a majority of them. Number one, CF prime of A is C times F prime of A, right? I can always take constant out of a derivative. Number two, f plus g prime of a derivative of the sum must be a sum of differences. F prime of a plus g prime of a. And then we have a product rule. F g prime of a is f prime of a, g of a plus f of a, g prime of a. And then we have finally the quotient rule, number 4. F over g prime at a is equal to f prime of a, g of a, minus g prime of a, f of a, divided by the square of g of a. And this should hold if g of a is not equal 0. All right, so we are ready to prove these properties. Again, as I said, some of them. Proof. At this stage, we don't know any of these rules, so we have to resort to using a definition. So let's do number 1. F CF prime of A. What is that? According to the definition of a derivative, this is a limit h goes to 0 of CF of A plus h minus CF evaluated at A, everything divided by h. All right, so what can I do with this? I can just first remember what is the value of the function CF at A plus h. What's the value of the function CF? It's a value of a function f multiplied by c. So this should be c f of A plus h minus c times f of A divided by h. And now when I examine this, of course, algebra tells me that I can pull out c from the top. So this will be c times f of A plus h minus f of A over h. And then the limit is also a limit of the product is a product of limits, and limit of c is a constant. So this is c times limit h goes to 0 of all this just f of A plus h minus f of A divided by h. All right. So far I'm just using properties with limits. But then if I examine the expression inside the limit, this is nothing but the definition of a derivative at A. So the whole thing then is equal to c times f prime of A. So 1 is done. I'm going to skip 2 and go straight to 3. So for 3, I want to compute function fg, take its derivative, and then evaluate the derivative of fg at A. How should I do this? Again, I have to resort to the definition, limit definition of a derivative. So this is limit as h approaches 0 of fg at x right? Not at x, sorry. Fg at a plus h minus Fg of a whole thing over h. And somehow I know that the answer is given to me by this product rule. So it involves derivative of f and derivative of g. Derivative of f is the thing that I've written down, but without any g's in it. And derivative of g is the same thing, but without f's in them. So here, because of the presence of f, then the limit, I don't really know what this is. And I have to then rewrite, I will attempt to rewrite this expression in a different form from which I could potentially extract derivatives. And I will use the same strategy that I used already during this lecture as well, in proving the previous theorem. What I'm going to do, well, first I'm going to figure out what exactly do I mean by fg of a plus h. Value of the function fg is product of f at a plus h times g of a plus h minus f g of a f g of a is f of a times g of a, everything divided by h. So here is what I'm going to do. To find the derivative in here, what I will need to do is I need to have not f of a times g of a, but maybe f of a times g of a plus h, because then if I factor out g of a plus h, I'll just have f of a plus h minus f of a over h left. And that's good. In this case, I cannot factor anything out because I don't have common factors between the first product and the second product. So here is what I'm doing. Still taking a limit when h goes to 0. I still have f of a plus h times g of a plus h. But once again, to get the derivative of f, I would prefer to have f of a times g of a plus h up here, right? Because then I can factor out g of a plus h, and I have f of a plus h minus f of a left, and that I can use to find the derivative. But because I subtracted something artificial, I have to add the same thing. So plus f of a times g of a plus h, and I still have my f of a g of a left here. So minus f of a g of a. And the whole thing is multiplied by or divided by h as usual. Okay, so h. So now I can group similar terms here. And things actually are not going to look that bad because what is this? This is the limit h goes to 0. Common factor g of a plus h. So I'll pull it out. And if I pull it out, what I have left is f of a plus h minus f of a times g of a plus h, right? G of a plus h is a common factor. And then from the second pair, there is a common factor of f of a. So plus f of a times g of a plus h minus g of a. Okay, so that is how my denominator can be written. It's the same form as before, and you divide this by h. All right, so I hope it is clear what we're trying to do here. Right, I'm just taking a definition of a limit and I'm simply rewriting the stuff on the top in some equivalent form. Okay, then by properties of limits, I should be able to write this as a limit h tends to 0 of the first fraction f of a plus h minus f of a divided by h, and there is an extra g of a plus h left, which I'm going to append in here. Right. And then I will need to take a limit of f of a. That's the thing that I can factor out. And what's left is g of a plus h minus g of a over h. Okay? All right, so now we can use properties of derivatives that I already proved, and properties of limits. If I have a limit of the product of two derivatives, so what happens to f of a plus h minus f of a over h? That goes to f prime of a, right? Times the limit of g of a plus h. I need to figure out this limit. Then figure out the limit of f of a. That's easy because f of a is just a constant. Times the limit of this fraction, and the limit of this fraction is g prime of a. So let me rewrite this. Limit. So I'm looking at the first term. It has two terms in it, g of a plus h and f of a plus h minus f of a over h. So this is a limit of the product of these two things. H to 0. Of f of a plus h minus f of a over h. Let's suppose that this product exists, this limit exists, then the limit of g of a plus h also exists and equal to g of a, right? That is a result of a continuity that I just proved in the previous theorem. So times the limit h to 0 of g of a plus h. Let's see if I'm missing anything here, right? So that's going to be the first limit plus a second limit. But the second limit is a limit of a constant, f of a, times this function. So again, the limit can be split. Limit h goes to 0 of f of a times the limit h goes to 0 h goes to 0 of g of a plus h minus g of a over h. So again, the first limit exists, n is equal to f prime of a. Second limit exists, and it is equal to g of a because g is a continuous function at a, and when h goes to 0, right, then the limit is going to be value of the function at a. This first limit down here is, of course, f of a because f of a is a constant. And times this limit, the last limit, and this limit is clearly g prime of a. And so that means that the overall limit should be f prime of a times g of a plus f of a times g prime of a, and that is a product rule. And I'll continue along the same lines in the next installment of this lecture.